we are, just not today. Because we're got our hands full getting ready for the quiz tomorrow. So I do have everybody finished up with it, so if we have some time at the end tomorrow, we may do that. Because I think we will have some time. I don't think the quiz should take a whole block, but we'll see how that goes. So we'll get a chance to look at them anyway, whether we go over them or not will depend on everything. All right, so the first thing we did was areas, just, this S-shaped symbol, the integral symbol means area. So we found some areas geometrically with triangles and half circles and stuff. But then we wondered, how in the world do we do an area under, say, an x squared? How would we find that area? And we started with the reason why we might want to find area, which was that velocity example. You view the area underneath velocity, that tells you how far you travel. So that's just one thing that we might be able to use it for. There's going to be more. As we get into other chapters, we're going to learn about that. But for right now, it's just, how in the world could we get to that area? So we did some work with that. Then we got into this whole area function thing. And then, of course, we realized the area function is the antiderivative of the function you're doing the area under. And then, of course, that led us to all these connections like we had with derivative about functions and increasing, all these mathematical kind of stuff. And so all this notation about that, and this fundamental theorem part 1, which again basically just says that the area function is the antiderivative, but that's a huge statement, and it brings with it all of this stuff. So we talk a lot about looking at old stuff in a new way. That's a big part of the quiz, is that. And that's what this homework was about. So really want to hear from you on what questions you have about that. So we can talk about that. And then the last small part of the quiz is finally answering that question. How do we find that area under, like an x squared? How do we do that? We're pretty sure the antiderivatives involved somehow, and it is. But how do we do that? And that's the new part we're going to do today, and then we'll practice. Your homework will be pretty much just that. But the quiz is, the homework's really not review for the quiz. The homework is just the one new thing we're doing today. But you'll want to go back and just kind of review all of those things we've talked about. Okay, so let's start with the homework. So I do want to talk about, did we talk about number 12 yesterday in class? 12 on 12 through 14? Didn't we? Okay, I couldn't remember if we did or not. So we talked about 9, 10, and 11 yesterday. That was this situation here, that we said that little f, was greater than 1, and they gave you big F and big G, right? So what we know is that big F is the antiderivative of little f, and big G is also an antiderivative. They're different in the plus c, right? That's how antiderivatives are always different. If I have the antiderivative of x, that's 1/2 x squared plus c. We figured out that the left edge is what determines that c, right? Different left edge, different plus c, because it's a different piece of area that they are apart. So that's what we know. So then we went through a series of questions about this. So question 12 said, show that g of x is equal to big F of x plus c. Well, what that's saying is that big G and big F are the same thing except for some constant, which of course is what we just got in saying. They're both antiderivatives of little f. We don't know what they are, but they're both antiderivatives of little f. They only differ by constant. So that much is obvious. So that's all you really have to say. But then they said, is C positive? What'd you say? No. And remember how we did that yesterday? We said, well, if big F is the red, that's the area from 0 to x. That's this area. And if big G is the blue, that's from 5 to x. That's that. Which one's bigger? The red. F is bigger. So if these two are going to be equal, C's got to be negative. Right? We got to take away some areas to make them equal. Specifically, we'd have to take away this piece of area here from 0 to 5. that would be the C. Okay, and it would be me. All right, but here's where the questions get interesting. 13 says, is big F of 6, so this is the kind of stuff I want us to be ready for tomorrow, to answer this. Show that big F of 6 is greater than or equal to 6. Somebody want to explain this one? See, we had our meeting, we had that early dismissal yesterday, and one of the things, I told you guys this earlier, but we're talking about questioning techniques and for teachers. And one of the things they said is if several people seem to answer all the time, or if I call on the same people all the time, that's not good. That's the popsicle stick strategy, right? So I should call on random people. Some of you are both putting your head down like this. Otherwise, you won't think of the answer because you know somebody else will answer it. So, Kelsey Stitham, haven't called on you lately. You answer for us. Go ahead, Kelsey. I'll be honest, I'm not a big fan. I understand the reasoning that is behind it, but I know when I was sitting in calculus class, there were times where I did not want to be called on, and I would not have been happy if they did. But go ahead.
I wrote down, doesn't it say that F is always greater than 1?
Little f is greater than 1.
And since F of 0 starts at 0, so then every time that F increases 1, but X, little f goes up by 1, big F has to increase by more than 1, since F is like the slope. F is the derivative of, little f is the derivative of big F. And so since it's always greater than 1, the slope of big F is always bigger than 1. So at x equals 6, F is equal to 2.
You are making a slope argument here.
That's not what I wrote down, but yeah.
I agree with that. I don't think that's a problem. That sounds awful familiar to me. The argument that she's making. It had a name.
Oh, speed limit.
It's a speed limit law. Now, we're in the middle of doing area here, so I want to also make an area argument here, but on the quiz tomorrow, if you make a slope argument on a problem, unless it specifically is asking about area, then that would be fine. So let me see if I can rephrase what I think Kelsey was saying. So, first of all, what would be some good things to say? One, here would be a really good thing to write down, I think, if you're going to make a slope argument, is that right there. Right? Because a minute ago we said big F is the antiderivative of F, little f. Well, that's a lot to write down. Doesn't that say the same thing? Okay, so if I have an area function like this, I'm writing that down. That gives me my connection. So that helps me with my explanation. Big F prime is little f. That tells me that this is, now, again, let's go back to speed limit law. Let's just talk slope here. Forget area. So this tells me that my slope is always more than 1. Now, the key to the speed limit law, and Kelsey said it, I don't know if you guys remember where she said that in there, but the key to the speed limit law is you had to know where you were starting. What did she say about where we were starting? Big F of 0 is, remember that free initial condition that we get? Right? Big F of 0, if you plug a 0 in for x right here, that's like putting an x right, a 0 right there. The area from 0 to 0 is 0. So if I had a big F graph here, we know it would start here. Now they're asking me about if I went over to 6. Well, since my slope is always more than 1, if I go over 6, I've got to go up at least 6. And so therefore, big F of 6 has to be 6 or more. Well, but that's that or part that we were talking about. You're right. Since F is always greater than 1, isn't it true that really F of 6 does have to be greater than 6, right? It won't be equal to. But isn't it okay to say that big F of 6 is greater than or equal to? It's okay to, I know every year people have trouble with this, and I even have trouble sometimes thinking about it. I think the example I gave earlier is if I have $1 million in my pocket, isn't it true for me to say I have greater than or equal to $10 in my pocket. It is true. Even though I don't have 10, I can say greater than or equal to, because or means one or the other, right? And so it's okay to say equal to here, but yes, it will not equal 6. So it would also be true to say just greater than 6, all right? Then they say, is it possible that g of 10 is 3? Oh, wait, time out. Area argument now. Let's make an area argument, okay? What else does big F of 6 mean now? Remember, new way of looking at old stuff. Big F means the area from 0 to 6. So if I go from 0 to 6, and I know the function has to be above this line, don't I have to have at least this much area? That's a 6 by 1 rectangle. So the area argument would be, big F of 6 is the area from 0 to 6, so, and I know that the graph is above 1, so I have to have, and I would draw a picture of this, and I would say, so I have to have at least 6 units of area or more, right? At least 6, so it could be 6 or more, and like we said, it really can't be 6. It's going to be more than 6, okay? So that would be your area argument. Don't have to do anything about slope. Speed limit law would be a part of it, but it's kind of cool to see, you know, we can make two seemingly totally different arguments for this one problem based on what we know about that. All right, g of 10, could it equal 3? Well, let's do the two arguments. Let's do the speed limit law argument. Let's do the slope. What is little f? No, but what is little f? As it relates to g? It's g prime, right? It's a derivative. Okay, so little f has to be more than 1. The slope has to be more than 1. But what you guys are forgetting, I think, is the free initial condition we get in for g. G of 5 is 0. The area from 5 to 5 is 0. So we know g of 5 is 0. So if I had a g graph here, it would start here at 5, 0. So if we're going to do speed limit law, if we're going to go over 5, we have to go up at least 5. So could g of 10 be 3? No way. It cannot be 3. It's got to go up more than that. If you go over 5, we know g of 5 is 0, so over 5, you got to go up 5. So g of 5 has to be more than 5, greater than or equal to 5. It cannot be 3. Let's do the area argument. If I want to do the area here, let's do it in this. So g of 10, another name for g of 10, or another way of thinking g of 10 is what? That's a 10 right there, right? Which would mean a 10 right there. It'd be the area from 5 to 10. Well, if I want to do the area, say this is 10 over here. I want to do the area from 5 to 10. It has to be at least 5. It has to be from 5 to 10 is going to be a 5 by 1 rectangle. And so that area's got to be at least 5. So it could not be 3. Okay? All right. So speed limit law or area now, either one of those arguments we could make. And the same is true in any of the chart kind of questions. We can make them. We can make those arguments using derivative, or we can now make them using area. And I would pick whichever one makes the most sense to you. A lot of times it's going to be the derivative argument because we're used to that. Okay, and that's okay. But we also want to think about areas. All right. I also wanted to talk about 24 through 28 real quick. That was the problem. That was the problem where we did yesterday, where we had f of x was equal to 3x plus 2, and then we had those other, we had big F, big G, big H. Now, actually, let's go to this. So let's talk about 24 through 28. That's back on that previous page, back on section 5.2, I think. Okay? It was this situation right over here. All right? So we were talking about this situation here. Now, 24, 25, 26. Did we do 24 through 28? Yeah, okay. So here was the scenario. Now, we had that this was, little f was 3x plus 2. Now, this is the kind of stuff that I may ask you again tomorrow, and I don't want you to make it harder All right. So if I graph little f, and this is one of the things we talked about, you need to be able to figure out. Now, it turns out that that crosses at negative 2/3, and you need to know that because of the slope and whatnot. You'd be able to figure that out. I said you just set that equal to 0 and figure it out. But that crosses at negative 2/3. This is little f. Every one of these is an antiderivative of that, right? Of course, that just answered question 28 for you, right? We knew that. That was easy. Now, the question is, where is big F increasing? When little f is positive. So that didn't use any area. We didn't have to use area at all there. Now, if you want to use area in that situation, I suppose we could pull this thing up from yesterday. This is going to complicate it a little bit to think about area. I think you're better off just thinking about derivative, and I'm perfectly fine with that. But yesterday we had this, let's see. All right, yesterday we had this, here's 3x plus 2, here's the graph 3x plus 2, and what's big F start? Left edge is what? Left edge is 0. Now, if I want to use an area argument, here's the best way to make an area argument for question 24. When is big F increasing? Big F is the area from 0 to x. Right now, this is my area from 0 to x. So I pull my left edge way over here to the left side. Okay, and now what is my area right now? Positive or negative? Positive, right? Because what's this area? Remember, I'm going backwards. Negative plus a bunch more positive. So right now I have positive area. As I slide, now this, I would not recommend you using this as your argument unless you feel real comfortable with it, okay, for question 24. But it would be nice to understand this. But it's a little more complicated way of doing it. But I want to show you that we can make a derivative argument, we can make an area argument for anything that's in the chart. Now, what is this area doing? Well, the area, as I drag this, what am I losing? I'm losing positive area. So what is my big F graph doing? Going down. Well, that's not what we wanted on this one, right? We wanted when it's increasing. So as I lose positive area, I lose it until there, which was negative 2/3. Then I start losing negative. What happens in the area graph if you lose negative? It goes up, right? So my big F graph is now going up, which is what we want, right? So it started right here at negative 2/3. And now once I get past here, I quit losing negative and I start gaining positive, but that's still a gain in area, right? So people get hung up with the 0, where the 0 is, or where the left edge is, as if that would change the chart stuff. It doesn't. The answer to this, where is big F increasing, is from negative 2/3 to infinity. It's when F is positive, which is the same thing we learned a long time ago. Big F is increasing when little f is positive, which is from here. But now, as soon as I would change this question to G, if I now ask where is G increasing, what would you say? Same thing. Because little f is the derivative of that function. But you say, but wait a minute, G starts at 1. Well, let's come back to this example. Right? Now, instead of starting there, let's start here. Well, now what's my area? Well, actually, it doesn't matter what my total area is. The thing is, whoops. Let's start dragging. What are we losing? We're losing positive. So my area graph would be going down until here. Then I start losing. I'm losing negative, losing negative, losing negative, losing negative, losing negative, which is a gain of area, until here I start gaining positive. Do you see where that left edge didn't matter? It just changed from losing negative to gaining positive. It didn't matter. The key was right here, right? So that left edge, when we're doing chart stuff, the left edge doesn't matter. Now, the reason it doesn't matter, another way of thinking, is, look at this here. I got off track of the problem we're on, but just What if my little f was this? Wouldn't this be, remember what we did back in chapter 1 when we would draw this? We would have little f and draw big F, remember that? Wouldn't this be right? Little f's positive, so this graph's going up. Local max right here, right? Everybody with me? This is little f, this is derivative, that's local max. Now it's decreasing till here, local min, right? But then here's big G, and so the new thing we've learned is different left edge, different C value. Isn't that just a vertical shift? See how I vertically shifted them? Now look at those two graphs, big F and big G. Where is this graph concave down? All the way to there. Where's this graph concave down? Same place, right? All the chart stuff doesn't change if all you do is a vertical shift. Concave up, concave down, local max, local min, increasing, decreasing, inflection point, that's all the same if all you do is shift it up and down. And when we change left edges, that's all we do, is we shift that antiderivative up and down. All right, so when we make those chart questions, when we answer them, we don't need to go and do that area thing about losing positive and gaining negative or blah, 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 whatever. We can just use our regular questions. Where is big F decreasing? When little f is negative. That'd be from negative infinity to negative 2/3 and so forth. Now concavity I kind of like. Big F is concave up when little f is increasing. Now, it's kind of cool to look at, and we'll just do it real quickly and then forget about it. But so when is this one increasing? Well, it's increasing all the time. Little f's always increasing, so our big F graph would always be concave up. Now, why is it concave up? Well, what's happening is when we're losing this positive area here, every time I slide this over, I'm losing smaller and smaller chunks of area. So what's happening as I come down, I'm not losing as fast. And so it's turning like this, and so it's concave up. Then all of a sudden, once I get past here, we said we were losing negative. So now it's going back up. But now what chunks am I losing? Bigger chunks. So now when I start losing negative, makes the graph go up, but it's becoming positive faster because I'm losing bigger and bigger chunks. And so that's why it goes up like that. So slowing down, then speeding up. Well, it was smaller chunks and it was bigger chunks. But again, the switch happened. Well, I didn't really switch. It was concave up that whole time whenever this was increasing. So it doesn't matter where this left edge is. Here I'm losing negative chunks bigger and bigger, and then I start gaining positive chunks bigger and bigger. And that's what makes it curve. And that's what makes it concave up. But again, bottom line is, when it's all said and done, it's just based on what little f is, just like it was before. So left edge changes, we don't have to worry about it. All this stays the same. All right. Anything else in the homework? 48? I figure that's one we maybe could talk about. And then if there are anything else, we could do it. But then I want to move on to the new stuff and leave you some work time. Okay? Quick review and so forth. Basically, what 48 says is this. It says the integral. No, I'm sorry. It says you're supposed to show that the derivative of the integral is not equal to the integral of the derivative. Now, don't worry about the t's and so forth, because remember, when it's inside the integral, you've got to have t's because you have x up here. When it's outside the integral like this, it'd be with respect to x, because that's your variable. But basically, it's saying, here's the derivative of the, I called it integral, but what do we know this is? The antiderivative, right? This is like saying the derivative of the antiderivative, and over here, it's like saying the antiderivative of the derivative. In other words, this question is really saying, does it matter which order you do it? Turns out the answer is yes. Okay? And so it does matter, so these are not equal. Now, what are they different by? If they're different because of the c. Now, this side should look familiar. What is that side? That's just little f of x. That's just fundamental theorem part 1. The left side is simply fundamental theorem part 1, what we said yesterday, which says the derivative of the antiderivative is just little f. Well, think about it. Why is that? Because what is this? This is the antiderivative, which would be like a big F of x plus some constant. Well, what happens when you do the derivative of big F of x? You get little f of x and the constant goes away, right? The constant goes away. So that's why fundamental theorem part 1 gives us that, because the inside is the antiderivative plus some constant, and then when we do the derivative, it gives us back the little f and the constant goes away. But if we do the reverse order, let's work through that. What's the derivative of f? So this would be kind of like saying this. Now what's the antiderivative of f prime? F of x plus some c. So what happens is if you do the antiderivative last, you have a plus c on it. If you do the antiderivative first, you have the plus c, but then when you do the derivative, the c goes away. So that's the difference. That's why they're not the same. That's why they're not the same. Okay? That's all that was about. It's just kind of a notation. But if you understand what we've been talking about, how this area functions, when you have this x up here, that's the key. When you have this x up here, it means antiderivative. It means antiderivative. Now look at this. If you don't have the x up there, now what does that mean? That's just a piece of area, right? And that's where we're going with the new thing. That's where we started this whole thing with, is how do we find that fixed piece of area? But we've been spending a lot of time in this section. How do we find, what is this thing with an x up here? Well, it's an area function, and that's where we learned about antiderivative. That's where the antiderivative stuff came from. All right. Anything else in the homework ones? Anything I've left off here that you wondered about?
We do 43.
What did 43 say?
Suppose that and it says evaluate f of 2.
Ah, yes, that's a good one. That's a good one. So it says little f of t. Is this the one? No. It says you read it to me. The integral
Yeah.
0 to x f of t dt minus cosine x, and find little f of 2. Okay, so as we've often said, before I can find little f of 2, I need little f of x, right? I need little f of x. Well, little f of x is this thing in here, right? That's got a t in it, but who cares about that? Remember, that t's just there because it has to be because of this inside. So what is it? So this goes back to what we were just saying. So what does this left side mean? The antiderivative of little f, right? So this means the antiderivative of little f. So is this. So this is like big F over here, then, right? So if this is big F of x, what's little f? The derivative of that. So little f would be 6x plus e to the x plus sine x. There you go. So, and then you plug a 2 in, right? So it'd be 12 plus e squared plus sine 2. Now this is going to be a no calculator quiz. You would just leave it just like that, right? Who knows what e squared is or sine 2, we just leave it. But this is the type of question I'm talking about that would be in there. And it's hard to study that other than just go back through this homework because, like I've been saying, it's a lot of just new ways of looking at old stuff. And the key to all of it is the area function is the antiderivative. You just keep that in mind. Any problem dealing with an area function, just keep that in mind. So when you looked at this, what you'd be thinking is, okay, this is the antiderivative of little f. And just call it big F if you want. You call it big G, big H, whatever, big A, whatever. So this is big F. So big F is that. Oh, okay, so little f would be the derivative, right? And that's your thought process. That's your thought process. And that should be enough to lead you into, if that's big F, then you can think of the chart or whatever is appropriate. Okay? And there you go. Okay, good question. Anything else? Yes. You're stretching. Okay. All right. So let's go on now to this question. The one new thing we have to do that kind of wraps all this up, because as you get ready to write this This is why we've done all this stuff with area function. Because this is really the question. We started off, our first day of integrals, we started off with that table of velocities, and we said, how far did this person travel? And we realized that, hey, that's the area under the curve. The area under velocity is how far we've traveled. We did that the second day of class, actually, back in October. We had that same problem. And we found that the area under there gave us something. So, we started off then by doing some trapezoids and triangles and stuff like that, and we quickly realized that our geometry is limiting for us, because here's an example of some area that we just don't know how to find. There's just no geometric formula to find that area. So we hope we've established, I hope I've established the fact that we might be interested in that area. It might give us some valuable information. And so, how do we find it? So what we did is we got into the whole idea of area function, treating it as a function. And then we found out that it was connected to the derivative. It's the antiderivative. And so, of course, then that brought in all of these old relationships we had with the chart and all that kind of stuff. And it brought in some new formulas with the integrals and things we could do. But the reason this is such a big deal, like I said before, in the 1600s, is these were problems trying to be solved. And when they connected, that made it kind of a big deal. So now we're ready to actually answer this question. How in the world can we find this? All right? Now, here's how we're going to do it. You do not need to write this down, this part I'm about to do. Because what we're going to do is we're going to develop the way that we're going to get this. But once we get it developed, then that's how you'll do it. You won't have to go through what I'm about to go through right now. Okay? So you can just sit and watch this part. All right? So what I've done is I've said, okay, we know the antiderivative. I want to find this area here, so let me write it as a couple of different area functions. Y -1 and y2, who knows? I just made those up. Okay? But I want to think about what we've learned about our integral notation. Well, one of the things we've learned is that I could take this area right here, and I could rewrite it as the area from -3 to -1, plus the area from -1 to 4. Isn't that correct? And the -1 wouldn't even have to be in between there, but, right? That was one of the little rules we learned. And another little rule we learned is if I flip these around, what does that do to the area? Makes it opposite. So I'll just stick a little opposite sign out there. So wouldn't this statement still also be true right here? So this statement here would be the same, right, as the area I'm looking for, right? Okay, now, this has a negative on it, this has a positive, so I just prefer to have those flipped around. So let me flip them around here. This would be -1 to 4, x squared dx, minus the integral -1 to -3, x squared dx. Everybody okay with that so far? Okay, and then I also remember that, oh, if this is big F of x, and it's the area from -1 to x, then what would be another name for the area from -1 to 4? That'd be big F of, wouldn't it? Right? And then this one would be the same as big F of -3, right? Oh, this is interesting. So this area would be this. Now, what is big F? Oh, it's the antiderivative of this function. Now, with x, not t, though, right? It's the antiderivative of this function. I think we learned how to do that, too. How do we do the antiderivative of x squared? It'd be, what would be the antiderivative of x squared? No, that's a derivative. 1/3, well, it wouldn't be t, though. Remember, it's x, right? When we talk about this antiderivative, it's big F of x, right? It's this. Remember, the t's just, when it's inside the integral, it's got to be t, or something else. But when we do the antiderivative or whatever, then it turns into x, right? Don't forget that. That's important. But then what are you missing here? Plus c. Now, how do we find the c? We know big F of is 0, area from -1 to -1. So now I could plug that in, so 1/3 times negative 1 cubed plus c's got to equal 0. So this would be what? Negative 1/3. So c would equal 1/3. So my big F function is 1/3 x cubed plus 1/3. Now, I'm going to plug a 4 into here. So this would be 1/3 4 cubed plus 1/3. And that'd be 64 thirds plus 1/3, right? Which would be 65 thirds. Right? With me? And now I'm going to find big F of negative 3, which would be 1/3 x cubed plus 1/3. And now let's put a negative 3 in. So 1/3 negative 3 cubed plus 1/3. That'd be what? Negative 27 thirds plus 1/3, which is negative 26 thirds. And then I want to subtract those. Well, that'd be 91 thirds. I just found it, didn't I? I just found that area. Just using stuff we've learned, I rewrote this integral. I split it into 2. I flipped that. We know that means negative. I moved them around. I used my notation. I got that. I found my c, right? And I did it. Now, here's the beautiful thing about this. You're not going to have to do all that. You're not going to have to do all that. Because I want you to look at something here. I want you to look at something here. When I plugged in that 4, well, here's especially the part. You're not going to have to do any of this. And you're not even going to have to do this. Now, on the quiz, I might want you to do this. I might, forget all this other stuff. I might give you this problem right here and say, find the formula for big F, right? We did that on our homework. Find the formula for big F. Well, you just say, well, that's the antiderivative plus a c, and then I got my initial condition, right? And I can plug that in, I can find the c. So if I need to find the c, I can. But I want you to look at this. I went through all that work to find the c, but then when I subtracted, did the c really matter? Because wouldn't that 1/3 have just subtracted out anyway? Really, I could have just done 64 thirds plus 27 thirds, and isn't that 91 thirds, right? So the c would have subtracted out here anyway. See, this big F would have had a plus c, this big F would have had a plus c, and when I subtracted them, those c's would have gone away. And here's the cool thing about that, is, again, at the beginning I said, where in the world did I get this big F with a negative 1? I just made it up, didn't matter. What if we'd have done the whole thing with G? What would have changed? Yeah, this would have been a 2. This would have been, yeah, this would have been a 2. This would have been a 2. So 2 to 4, that would have been big G of 4. And 2 to negative 3, that would have been big G of negative 3, right? And G would have a different C than F, right? Because it's got a different left edge. But that would have subtracted out anyway. So here's the beautiful thing. Yeah, to get this, all we need is an antiderivative. Does it matter which antiderivative? Any old antiderivative. The C doesn't matter. All we need to get this area is take any old antiderivative of this, plug in a 4, plug in a negative 3, subtract them, and we got our area. That's a beautiful thing. That is almost as cool as Fundamental Theorem Part 1. Not quite as cool, so we're going to call it Fundamental Theorem Part 2. Okay? It's not quite as important, so it's going to be Part 2. Now, to be honest, when I learned it, when I was in high school, this was Part 1. Some books call this Part 1 and the other one Part 2. While you're writing that, I'll just talk about that a little bit. Part 1 is important because of what it means. Part 1, what does Part 1 tell us? What did Fundamental Theorem Part 1 tell us? Yeah, it basically told us the area function is the antiderivative. I mean, that's a huge deal. Without that, you can't do any of the rest of it, right? So that's why I think most books now call that Part 1. Because without that idea, right, you can't do any of this. But that's what it is. It's just the big idea. It's not very useful. This part is the one we were looking for, right? This is why we started all this stuff. is because we wanted to be able to find an area from A to B, right? And so this is the most useful part by far. Without part one, though, we couldn't have got part two. Okay, so some books call this part one because it's so useful and it's the it's the one we work with the most. Okay, but basically what this is saying is to get any area under a curve from A to B, you simply do the antiderivative. Doesn't matter which antiderivative you do. Well, they're all the same except for the C, right? So just pick the one where C is 0, where there's no plus C at all. Plug in the top number, plug in the bottom number, and then subtract. And voila, you've got the area under the curve. Now, it's kind of cool to try that with one where we already know what the answer is. For example, if I had a line, let's say, well, the other day we did this line 3x plus 2, right? And let's say we were going to do the area from 0 to 4. That would be this to this. That's a trapezoid. Now this would be 2. What would this side of that trapezoid be? At 4. 14. So this area would be 1/2 2 plus 14 times 4. So this would be 16 times a half would be 8. 8 times 4. This would be an area of 32. We know that from geometry. But this would also be this problem right here. Now, earlier, when we first learned about integrals, when we saw something like this, a lot of times we would maybe split it up. We talked about splitting it up and stuff like that. Well, it's not really a problem with this. We're not going to split that up. There's no need to. Look at the new thing we've learned. The new thing we learned, and let me show you how this looks. The new thing we learned says all we got to do is the antiderivative of this. So what is the antiderivative of that? No, not x cubed. Oh, let's review that. How do we do the antiderivative of x to the n power? How do we do the antiderivative of a power? We raise it up 1, and we divide by that new power. It wouldn't be x cubed because if you check that and bring the 3 down, it'd be 3x squared, right? You raise the power 1 and divide by the new power. Now, let me stop here just a second. On the quiz tomorrow, there will be just a couple of these where we're going to do this fundamental theorem part 2. Because that's more for our practice when we get to the gateway of doing a bunch of antiderivatives. Obviously, antiderivatives are important now, we can see, because that's how we do these integrals. So we need to be able to do antiderivatives. We're going to keep it to just some basic ones like power rules or sign or something like that. Okay? Now, so back to this. So what's the antiderivative of 3x? 3/2 x squared. You raise the power up to a 2, and then you divide by 2. 3/2 x squared. Plus, what's the antiderivative of 2? 2x. Now, here's how I want you to write this. Here's how I want you to show your work. Because remember, this is no calculator. So what we're going to do, we're going to use what I call right bracket notation. Okay? So what I've done is I've done the antiderivative of the function inside, the little f. I did the antiderivative. I didn't worry about the plus c, right? Why? It's going to subtract out anyway, right? So it doesn't matter. And now sometimes people will say, well, what happened to the dx? Or something like that. Well, think about this now. If I ask you to do the derivative of x squared, and I wrote it like this, if I just said do this, what would you write? 2x. And you wouldn't think about a dx being on there. You wouldn't say what happened to the dx, because what this was saying was do the derivative with respect to x. So you did. Well, what this is saying is you want to do this integral, you do the antiderivative with respect to x. So that's what we did. So the integral sign goes away, right? The dx goes away. And now, and then, so what I like to do, I call this, or your book calls it right bracket notation. Okay? So I think it's a good way to write it. So do your antiderivative. Put your 0 and your 4 there, and now we're simply going to do what this rule says. We're going to plug in the top one, we're going to plug in the bottom one, and subtract it. Now, some people try to do too much in their head, and they kind of mess up some stuff. This would be 3/2 times what? 4 squared plus 2 times 4. Okay, that'd be the first part. And then minus, and then 3 halves, 0 squared plus 2 times 0. Now it turns out, since I picked 0 in there, it turns out that last part just multiplies out and just ends up being 0 anyway, but that's just kind of lucky. A lot of times it doesn't. And if you don't put parentheses around this last one, that minus sign will get you in trouble. Okay, and I've seen people get in trouble with that. Okay, so anyway, we get 16 times 3, that'd be 48 halves, what's that, 24, plus 8. This is 0, and what do you know, 32, which is the same thing they got over there. Okay, now you might argue on this one it'd been faster to do the trapezoid than it was to do this, I don't know. But not with a lot of problems, right? And then, of course, with parabolas, stuff like that, you wouldn't be able to do it anyway. All right. All right, let's do a couple here that are in your homework, and I'm going to give you a lot of work time today. Matter of fact, we're just about done here. I do want to talk about the just the quiz overall here in a minute. But let's just do a couple of quick ones that are in your homework. So, oops. So just so we can see, here we go. Okay, so here's going to be your homework. Here's going to be your homework, which is to finish the 5.3. I think 5.3 we did 1 through 8, and then we did like 35 through 38, and then we did 43 and 48. So I think that leaves you like 19 through 30, and then it leaves you a few others at the end, 49, something like that. Okay, so finish what your assignment sheet says is left on 5.3, and then in the LH packet, page 298, 3 through 36, multiples of 3. 3, 6, 9, 12, so forth, so that's like 12 problems. Now, every one of those, I think, or pretty much every one of those, is just this fundamental theorem part 2, right? Just finding these areas. But that's a small part of the quiz tomorrow, right? A big part of the quiz is that whole area function, antiderivative chart, that kind of stuff. But I'm going to give you a chance to jot that down here in a minute as it relates to the quiz. All right, so let's do a couple of them here. So we'll just do a couple of them simultaneously, maybe. Okay, here's 2 of them. This is in that section that's 19 through 30 on page in this 5.3 section. Okay, so I got one of them over there is the integral from 0 to 4 of square root of x dx, and the integral pi halves to pi of sine x dx. Okay, now I've drawn pictures of those. You don't have to draw pictures unless the problem says to draw pictures. I may on the quiz ask you to draw a picture of a simple graph. We should know what the square root graph looks like. We should know what the sine graph looks like. Okay, but I just want you to get a sense of what it is you're doing, what it is you're finding here, right? So we're finding this piece of area. We're finding that piece of area. Now, interesting thing about this one, we already know what the area under the hump is. We had that one problem where they told us it was what? 2. So if we go from pi halves to pi, better be 1, right? We better get 1 as our answer. But until today, we didn't know how we would do either of these areas because they're not geometric shapes. So what are we going to do on 20? Let's do 20 here. Antiderivative. How do you do the antiderivative of square root of x? So we think of it as x to the 1/2, so we raise that up 1. It would be x to the 3 halves, and then divide by 3 halves. So that'd be 2/3 x to the 3 halves. And then plus c, but we ignore the c, right? Because we're going to subtract it out anyway. It'll subtract out anyway. What's the antiderivative of sine? The antiderivative of sine. Negative cosine, right? And the way you do an antiderivative, at least for right now, is you just think, what would happen if I did the derivative? Well, if you can't choose cosine, because you do the derivative of cosine, that's negative sine. So it's negative cosine. Okay. So here's how I would write those in. Write your antiderivatives, no plus c on them. Right bracket, right? Right bracket. And then put on those numbers. Okay? Now, I'm not saying you have to have that step right there, I just think it's nice notation to use, but that's what you're going to do. You're going to take that antiderivative, and now you're going to plug in the 4, plug in the 0, and on the other one, you're going to plug in the pi halves. Go ahead and try that. But notice, once you do the antiderivative, the integral symbol goes away, the dx goes away, because that was just telling you, here's what you should do. Do the antiderivative with respect to x, right? And so once you've done that, the integral symbol's gone. But we have not practiced antiderivatives a whole lot. So that's why on the quiz tomorrow, there's just going to be a couple, right? There might be one that gets into some fractions and stuff like that, like this 3/2 one is going to here. You know, so you got to be able to do it, but it's not going to be a huge emphasis. That'll be next week. All right. And what are you coming up with? 16 thirds. So you'd have 2/3, 4 to the 3/2, and of course 3/2, that's square root. Square root of 4 is 2. 2 cubed is 8. 8 times 2/3, 16 thirds. 0, of course, is just 0. So you get 16 thirds. Over here, now, negative cosine of pi, negative cosine of pi half, so we got to know those. Cosine, of course, cosine graph looks like this. So cosine of pi, that'd be down here at -1, or you use the unit circle. The opposite of -1 would be 1. This turns into plus. Cosine of pi halves is right here at 0. And sure enough, we did get 1. We did get 1. Okay? Which is what we thought. All right. So I'm going to let you go to work. I mean, that's over a half hour now. Oh, no, I told you I was going to do some, show you a quiz thing here. So let's do that. And then you're going to have a bunch of work time. There might be a couple that get a little tricky with antiderivative. I'll help you with a little bit. But they won't get that tricky on the quiz tomorrow. All right. So here's what I've got down as it relates to the quiz. So, kind of tie it all up here. Section 5.1, we started out saying, hey, we want to find these areas. Well, what areas do we know about? Well, we know about geometry. Triangles, trapezoids, rectangles, squares, half circles. So that's when you had these piecewise type functions like this, right? And you had to find some areas. So you'll probably have to do that again. Now remember, you may have to find where this line crosses the x-axis. It might not be at a nice, neat point, but you'll be able to figure the slope, and you need to be able to find where that is. So it might get messy, might be some fractions, stuff like that. But we want to be able to find these areas. Okay, that's also when we learned those formulas for splitting up integrals. But like we said, now that we know this fundamental theorem part 2, we probably don't need that as much, but you still might get a problem like this. You still might get a problem that says, what's the integral from 2 to 5 of 3 h of x plus 4 f of x dx, and in the directions they tell you that h of x, the integral is -3, and, from 2 to 5, the f of x is, 7 or something like that. And so you may still get a problem where you would want to take your integral and split it apart, and do that, and be able to use those. So that may come into play a little bit, okay? In a problem, something like that. So that's basically what we did in section 1. We were just learning about notation for finding areas. The main part of the quiz is this middle section, right? All that stuff we've been doing now for several days with area functions. So that's when we put that x up there in the top of the integral. And we learned that it was the antiderivative. We got fundamental theorem part 1, which tells us that the area function is the antiderivative. That lends to all these chart kind of questions, and speed limit law, and all those different types of things. A whole variety of things there that you could be asked, just like what your homework's been the last few days. How the left edge determines the plus c part of the antiderivative, right? And then another small part of the quiz would be this newest thing then that we just said with this fundamental theorem part 2, finding, big F of B minus big F of A allows us to find any type of area as long as we can find the antiderivative. Okay? So a little bit of that you might have to do as well. Okay? So, that is that. I wanted to get through that And I think we covered it pretty well. So you could have some work time so that you can now ask some individual questions if you need to. You can work together on that homework. That homework really is just this last thing, okay? Fundamental Theorem Part 2. So you can get into that, but you know, there's a lot more to the quiz too, some of this old homework. So if you've got questions on the things we haven't answered, you can ask individually or talk with each other about them. Okay? All right. So did everybody get that down, the homework? LH 298, 3 through 36, multiple of 3, and the rest of 5.3. Go ahead and work. Yeah.
Whoa.